Thank you, Nivaldo, for the presentation. And I also would like to thank the organizers of this thematic session for the invitation. It's a pleasure for me to be part of this. As Nivaldo told, I'm a former student from Singularity group in São Carlos, and now I'm part of this big group, and it's a pleasure to me to be part of this meeting. So I'm going to give you an overview on structurally unstable quadratic differential systems of codimension 2. It's not closely related to the theory of singularities, but we use some of these. I'm going to talk more about dynamical systems, and I'm going to show you where we use singularities here, okay? So let's start. My collaborators in this project are João Carlos Artes from Spain, Regilene Oliveira from Brazil, and also Marcos Mota from Brazil, okay? Feel free to interrupt me and make any question. So I'm going to introduce you the progress of the study on the classification of the structurally unstable quadratic differential systems of codimension 2 modulo limit cycles. I'm going to translate this into English. What does all of these words mean altogether, okay? But first, I'm going to make a question here. I'm talking about classification, quadratic differential systems, codimension 2 modulo limit cycles. But classification here, I mean that I'm considering all the phase portraits of quadratic differential systems of codimension 2, and I'm classifying all these phase portraits. And the question is, how many topologically distinct phase portraits of codimension 2 modulo limit cycles are there? Can you think of a number? And at the middle of the talk, I'm going to show you some results on this slide, okay? Think of a number. So let's translate all this title of my talk. We consider a polynomial differential system in the plane given by x dot equal to p of xy and y dot of equal to t cube of xy, and we call it QS. So it will be mostly in this talk, I'm going to refer to this system as a family because I'm not fixing the parameters. I'm considering them to be free, okay? And I'm considering here to be quadratic. These polynomials here, P and Q, of degree 2 in the variables X and Y. So for example, here we may have P of XY equals to A plus bx plus cy plus dx squared plus exy plus fy squared. And Q, something like this, okay? I make a remark here. When we consider singular points of this system here, since it is of degree 2 by Visu's theorem, system QS possesses at most 4 real simple finite singular points and 3 pairs of real simple infinite singular points, or 6 infinite singular points. One thing that is important here is that I'm going to show you some phase portraits in the Poincaré disk. What does it mean? I consider the plane R2, and I make a compactification here. Okay, here I consider the flow of the system, X, for example, and I make the compactification, and then we end up in a disk which is compact. So the plane R2 is compactified in the Poincaré disk. Poincaré disk. And when I say for real simple finite singular points, I mean that all these four singular points, finite, are in the affine part of this compactified plane. And the pairs of real simple singular points, let me change the color here, for example, orange. I have this pair here, another pair, and this other pair. So this is what I mean by this remark, okay? When we say that a property possessed by a differential system is called stable, it means that this property remains after a small change of the system itself. A classical example of this phrase here, this notion, is given by the Hartmann-Grobman theorem. If you have, for example, if a quadratic system possesses a hyperbolic saddle, Hartmann-Grobman theorem assures that for any suitable small perturbation of the system, the hyperbolic saddle persists after this small perturbation. So, for example, if you have, it's classical, this picture, if you have some saddle not too straight, we can make it straight using Hartmann-Grobman theorem due to the fact that we have a hyperbolic saddle, okay? So the property of possessing a hyperbolic saddle by a quadratic differential system is stable under small perturbations, okay? So this is what I mean about structural stability, okay? In this line, we continue here. We consider all the codimension zero quadratic differential systems, or the structurally stable systems, modulo limit cycles. So for a phase portrait to be of codimension zero, it must possess a finite number of hyperbolic singular points. So at most 10, 4 in the affine part, and 6 at the infinite, and no separatrix connection. So if the phase portrait or the quadratic system, for this phase portrait, these two conditions hold, so we say that this phase portrait is of codimension zero, okay? Now we add one more codimension. I think that something, it's not working, my screen. Is anyone hearing me?
Yes, Alex.
Yes.
Codimension zero, it appears over there. I have changed the, let me start over. Something happened here. I lost my connection. My Just a second.
We see you, Alex, and we hear you.
But my presentation, I cannot see it anymore.
Oh,
I think it's... just a second, stop sharing. Okay. Sorry for this.
No, we don't see
Nothing.
Not yet.
Oh my. No.
I don't think so. Not yet.
No. I'm going to show here.
It was black. Now we can see you. Okay. Yeah. Now, yes.
Okay. Let
Black.
Let me abandon the iPad and use only the computer. I cannot interact anymore. Sorry for this. So I was here. Okay. So a codimension 0 phase portrait means that we have only a finite number of hyperbolic singular points and no separatrix connection. But in codimension 1, we consider or we allow the break of only one stable object. What does it mean? That we still have a finite number of singular points, but here we allow the presence of a semi-hyperbolic singular point and only one, and or only one separatrix connection. If you pass to codimension 2, we allow exactly 2 codimension 1 objects, which should be 2 semi-hyperbolic singular points, or 1 nilpotent singular point, or 2 distinct separatrix connections, or 1 semi-hyperbolic or nilpotent singular point, and 1 separatrix connection. So in each step of codimension, we allow the break or the presence of one object of the codimension less one. Okay? And the quotient modulo limit cycles, which I say here, means that any nest of limit cycles is topologically equivalent to a focus having the stability of the outermost limit cycle. For example, here, if you have this nest of limit cycle, we have here a stable limit cycle and an unstable limit cycle. If we pass the quotient modulo limit cycles, all of these elements here shrinks to a point, and the stability of this point is the stability of the outermost limit cycle. So it is unstable, so this focus is unstable. On the other side, here, this outermost limit cycle should be drawn in blue. So since it is stable, the focus here after the quotient modulo limit cycles is stable. Okay, this is the modulo limit cycles that I put here. So all the phase portraits in my classification, the first part of my talk, will not contain any limit cycle. Okay. Hundreds of published papers deal with specific families, and they try to contribute to the general classification of this such big family of quadratic systems. For example, here, we have quadratic systems with a center or with no singular points, or homogeneous quadratic systems, and so on. Here I highlight the structurally stable quadratic systems that I'm going to talk more about it. And some of my contribution to this project since 2013. I classified the quadratic systems possessing a semi-elemental or a semi-hyperbolic triple node, saddle nodes, a finite and an infinite saddle node, and so on. And also these structurally unstable quadratic systems of codimension 1, which was a big work that I'm going to show you. All these papers that I have just mentioned deal with subclassification of quadratic differential systems. And some methods used before 1998 to obtain the total classification of quadratic differential systems was not very much effective. Rain, this author here, and his collaborators started classifying the quadratic differential systems from the most degenerate systems. But their work was proved to be incomplete, and in fact, some of the points are wrong and there are some gaps. So the attempt that we started, well, not me, but my group, is consider the most generic system and go to the most degenerate one. And we perform this study by the codimension in the structural stability of systems. Okay? So, how is this classification going? In 1998, Artes, Coy, and Gibra published this huge paper in the Memoirs of the American Mathematical Society, and they classified all the structurally stable quadratic vector fields, so the codimension 0 quadratic systems, and they proved that there are only, or this number, 44 topologically distinct phase portraits of codimension 0. Okay, so if you think about any structurally stable quadratic differential systems, if you draw it, it is one of these 44 phase portraits. Okay, 20 years later, in 2018, Artes, Gibra, and me published this book here in Birkhauser, where we classify the structurally unstable quadratic vector fields of codimension 1. So, and we proved that there exist at least 202 topologically distinct phase portraits of codimension 2, and at most 209. This plus 7 means that there are 7 phase portraits that we conjecture that is impossible to be realized by a quadratic differential system. What does it mean? That maybe, and we are almost sure about that, there is no quadratic differential systems in the plane whose phase portrait is one of these 7 phase portraits here. And we give at least 3 reasons why we think that they are impossible to be realized. Okay, if you want to see in a deep way this work, this book, you can email me and I can send it to you. Okay. So the codimension 1 quadratic systems is divided into 4 sets, A, B, C, and D. And in set A, for example, we consider the phase portraits where there are a coalescence, a collision, a coalescence between two finite singular points. So here, all the finite saddle nodes is inserted, included inside set A. Set B are consider or gather all the phase portraits which has a coalescence between two infinite singular points. Set C, we consider all the phase portraits which has a coalescence between a finite and an infinite singular points. And D, all the phase portraits which has a separatrix connection. And in each one of these sets, we have these numbers of potential phase portraits. What does it mean? For set A, we have 77 phase portraits, which is possible to be drawn, topologically speaking. But only 69 of the 77 is realized by a quadratic differential systems. And this happens to all of these, all the other classes. And this +7 here is those conjectured to be impossible. And we end up with at least 202 and at most 7, okay? So here are the sets of codimension 1. To consider the potential phase portrait of codimension 2, we have to combine, topologically speaking, phase portraits of codimension 1. So we consider phase portrait of group AA. What does it mean? We consider two coalescences or two collisions of finite singularities. Or we can consider a finite collision, a finite coalescence, and an infinite coalescence. Or two infinite coalescences, or even a finite coalescence and a finite to infinite coalescence. And we have all these groups here. And in group which possess D, we have some more cases. And in this set DD, you have 15 cases where we can consider these 5 types of separatrix connection. Or we have a loop, or we have the coalescence of the separatrices of two saddle, for example, or to a finite saddle to an infinite saddle, or to infinite saddle, which are symmetric, or to infinite saddle, which are adjacent. Okay? Sorry, I would draw this, but I cannot have this, the iPad now, sorry. So now the state of the art, how is this work going? Set AA is already published. It was published in 2020. And we proved that there are 34 topologically distinct phase portraits of codimension 2 from set AA. What does it mean? That here we allow 2 collisions of finite singular points. For example, we have a cusp point, or we have 2 saddle nodes, 2 distinct saddle nodes, or we have a topological saddle or a topological node. Here I bring some examples, the phase portraits. For example, here we have this phase portrait with only the cusp point at the finite part. And until 9, we have cusp here, another cusp, and until AA 15, we have cusp points, and the other A19, we have two saddle nodes. So here we have one saddle node and another saddle node, and so on. So here we have the 34 phase portraits, and they are all topologically distinct from each other. Set AB and AC is already published this year, and we proved that in this family here, AB, which we consider a finite saddle node, an infinite saddle node of type 0, 2, which means that two infinite singular points has collided. We have 7 to 1 topologically distinct phase portraits. And the other case, which we have a saddle node at infinity, which is the coalescence of a finite saddle to an infinite node or vice versa, we have 40 topologically distinct phase portraits. And just to give you a hint how we do this topological study is this way. We consider the codimension 1 phase portrait. So here consider A19 of codimension 1. Since it is from set A, we have a finite saddle node, and we want to obtain a phase portrait of set AB. If we already have the saddle node, so we have to coalesce infinite singular points. So I coalesce this point here with this, and this point with this point. So first, coalescing this saddle with this node, we have this phase portrait. Of course, we coalesce the symmetry point, it comes here. And we have this phase portrait. And if we consider the unfolding of codimension 1, it means making this saddle node at infinity disappear, we have this phase portrait of codimension 1. And in the other way, coalescing this node with this saddle here, we have this phase portrait, and the unfolding of codimension 1 is this one, which is topologically equivalent to this one. And of course, these two are topologically distinct, and they are realized by quadratic differential systems. This phase portrait here of codimension 1, A25, one of its unfolding of codimension 2 is possible, is realized, which is this one. We coalesce this singular point with this one. But the other possibility, coalescing this node with this saddle, we have this phase portrait, which is possible to be drawn. But if we consider its unfolding of codimension 1, making, separating this saddle node here, we have this phase portrait, which is already proved to be impossible. So if one of its unfolding of codimension -1 is impossible, then the codimension +1 is also impossible. So we have a codimension 2 phase portrait here, whose unfolding of codimension 1 is impossible. Then this is impossible. We have proved this result in our works, in our papers, and in fact it holds for codimension K. Okay. Here are other examples. From this we have here from set C, we coalesce finite singular point with infinite singular point. So here we have saddle node, this point, and we coalesce this saddle with this node here. We have this phase portrait, and then the unfolding, the node appears here in the affine part. And we make this game, we play with these phase portraits, topologically speaking, and after we look for realization of these phase portraits. Okay, here are other examples from set AC, but let me be a bit more quick here. Set AD, which deals with separatrix connection, is in progress. We have at least 79 topological distinct phase portraits, which is possible to be drawn, and we have to look for the realization. Set BB, we have these two elements here, a topological node and a topological saddle at infinity, which works like a hyperbolic node and hyperbolic saddle. And these since they are equivalent to some codimension 0 phase portraits, we don't consider them in our papers. We mention, but we don't consider them in the computation, in the final number. And here we have at most 9 topologically distinct phase portraits. BC is also in progress, and we are dealing with collision at infinity, 2 points at infinity, and a collision from 1 point at the finite part with an infinite singular point. And here we have at least 16 topologically distinct phase portraits to be drawn. And now the number that I asked you in the very beginning of my presentation, do you remember the number you chose? Codimension 0, we saw we have 44. Codimension 1, we saw that we have at least 202. And for codimension 2, the number, could you sum all the numbers, all the numbers I gave? We have at least 195, because we have some work in progress. And in fact, we have representatives of all these codimensions. So we have 265 for codimension 3 and so on. These elements. Of course, I'm considering here all the potential phase portraits, the one which is possible to be drawn, okay? And in sum, we have 927 distinct phase portraits of quadratic differential systems, modulo limit cycles, okay? We guess, or we wonder if this number here will increase or not. And we think that it will be something like this. This belly here means that these three sums here could increase. And codimension 3, we bet that we will have the more phase portraits in this codimension. Okay, so what is important here, now talking a little bit about the singularity theory in my work. We use the Sibrisky School theory of invariant polynomial in this project. What does it mean? These two help in classifying topologically subfamilies of planar quadratic differential systems. For example, systems with finite saddle node and infinite saddle nodes. And I'm going to pass here, I have 8 minutes more or less, how we do our classification of subfamilies of quadratic systems. So let's consider here this system, this normal form 1 here. It possesses a finite saddle node and an infinite saddle node constructed by the collision of a finite singular point with an infinite singular point. So we call this family QSN SN11, and this B is because this family can be split into two normal forms, and I'm considering only the normal form we call B, okay? And we have here 4 parameters, which are real, and this condition here must hold. Otherwise, we have degenerate phase system, okay? And what I'm going to show you is the classification of the phase portrait of the closure of this family here. And the theorem that we have is that we have 226 phase portrait of this family, of the closure of this family here. Okay, and all of these 226 are topologically distinct from each other. This system depends on this parameter, which belongs to R4. And if we consider the one of these C, E, H, or M non-zero, then we can apply this transformation and reobtain the same parameter C, E, H, M with a rescale, okay? So instead of considering the set R4 for our bifurcation diagram, we are going to consider the real projective space RP3. And why do we do this? Because this space is compact and everything is good in compact space, okay? And we are going to choose H, the parameter H, to be 0 or 1 and have this RP3, okay? So our bifurcation diagram is inside a sphere, and planes M is equal to M0 are constant. So we are going to make slices in M, okay? The open half sphere here, H is equal to 0, is the infinity of our RP3 or R4, okay, in the quotient. And we are going to give you the pictures of these slices M, or in affine charts, or in disks, okay? And when we are in a plane M constant, the coordinates are C and E. So how do we use invariant theory from Sibisky school? It was presented to my group by Professor Nikolai Vub, which was one of Sibisky's students. And the important contribution to the classification is that the former results were non-intrinsic. What does it mean? They depended on a convenient normal form. But now, using the invariant theory, our results are intrinsic or ideast. We don't need to have a specific normal form to use this invariant theory. All the results are intrinsic. And this is a great advantage because we can use all these invariants and apply to any normal form that we want. Here we have invariant polynomials, which are polynomials which have the variables of these invariant polynomials are the parameters of the system, and committants, which also depends on X and Y. And the diagram bifurcation will be constructed by some manifolds, which are the zeros of invariant polynomials, zeros of committants, and we also have some non-algebraic manifolds which are numerically found. I'm going to give you an example. Why this invariant theory is important? Because we can translate geometrical properties of the system into the zeros of polynomials in the variables of the systems. So we can control algebraically using invariant theory when a singularity goes to infinity, or if two singularities coalesce, or if there exist weak singular points for foci or saddles, if the line at infinity is filled up with singularities and any other geometrical property, it can be algebraically expressed, okay? So, for example, we have these two surfaces here. Green, we have a cusp type. Yellow, we have a weak singularity, and they are given by the zeros of these polynomials here. This surface here means that two singular points at infinity has coalesced, and it is this shape, in this shape. This bifurcation surface here means that a node is becoming a focus and vice versa. And next, having all these equations here of the surfaces, we studied the singularities, intersections, extrema of these surfaces, which are complicated most of the time, and mainly this W4, which is generically of degree 16. And for this normal form, this specific normal form, we found 54 important slices to be studied. And in each slice, we consider here, for example, we have m is equal to 4, which is the most generic slice in our diagram bifurcation. These are the algebraic surfaces. And we consider also the non-algebraic surfaces, which appears by continuation and coherence in the diagram bifurcation. And we found here, for example, we have some non-algebraic, which is in purple. This region here means that we have a limit cycle. It's important to mention that this specific subclassification, we are not doing it model limit cycles. And what I would like to show you is this. This is the most generic, and we can consider approximated to infinity and obtain this slice at infinity, which is coherent, this transition. And to finish, here, I would like to show you some transition in the work. If you consider, for example, this phase portrait, V88, we have a finite saddle node, an infinite saddle node here, and a focus, okay? If you cross yellow, it means that a Hopf bifurcation will happen. And then a limit cycle will be born here when we cross this line here and enter this region. And we have this phase portrait V88 with a limit cycle, which is V87. Crossing again this line, this yellow line, from this part, yellow part here means Hopf bifurcation. From here to here, a limit cycle was born. So from here to here, we thought that this limit cycle would be dead, would disappear. But no, another limit cycle was created. Why does it happen? Because on this line, we have a point which corresponds to a quadratic system with a weak focus of order 2. So somewhere next to it, we have a limit, a phase portrait with 2 limit cycles. And this is algebraically detected. And from this phase portrait, which has 2 limit cycles, to this one, which they are neighbors, 2 limit cycles to no limit cycles. What should happen? These 2 limit cycles would coalesce and create a double limit cycle, which is a geometrical property, a non-algebraic geometric property, and then crossing from here to here, these 2 limit cycles coalesce, becoming a double limit cycle, and then it disappears when we enter this region V88. Okay, so here I would show you another transition. We have also a region with 3 limit cycles, but my time is over. And here are some families to be studied, and some references I use it in this presentation. Others are inside the talk, and thank you very much for your attention.